Suppose we should get started then. So okay, hello everyone. Thank you for attending the virtual colloquium today. I'm Zach Zoe. I'm a second year PhD student here at UW-Madison, and the president of the Informed Student Chapter here. And on behalf of the Informed Student Chapter, it's my pleasure to introduce Dr. Phebe Vayanos. Dr. Vayanos is an assistant professor of Industrial and Systems Engineering and Computer Science at the University of Southern California. She's also an associate director of the Center of Artificial Intelligence and the Society at USC. Her research is focused on operations research and artificial intelligence, specifically optimization and machine learning. And her work is motivated by problems that are important for social goods. Today, we're fortunate to have Dr. Vayanos here, and she'll be speaking about her research on active preference elicitation via adjustable robust optimization. So Phoebe, I will turn it over to you.
Thank you so much, Zach. Thanks for inviting me and thanks for the nice introduction. I'm still gonna need to be able to share somehow. It seems when I gave when I made Jane a host, I also gave away my sharing rights.
Okay, let me take care of that for you. You should. Are you sure you're not able to share? Let me.
Yeah, host disabled participants.
Maybe make a co-host, Jane.
Oh wait, I got it. I got it. There. You should have it now.
All right. Yeah, that works now. Perfect.
Okay. Thank you. Sorry about that.
Yeah, no, you're good. Is this working? You guys can see my full screen? All right, wonderful. So thanks again, Zach, for the introduction, for the invitation. I really appreciate it. I'm super excited to be here. It's, I guess, my first time presenting the University of Wisconsin-Madison, so thanks so much. It's nice to see some familiar faces, some new faces, so I'm really, really happy to be virtually here. So what I'd like to do today is tell you a little bit about a recent paper of mine on active preference elicitation via adjustable robust optimization. And this paper was actually motivated by my collaboration with the Los Angeles Homeless Services Authority and with the problem of trying to design policies that better align with stakeholder preferences and that help allocate basically housing resources to those experiencing homelessness. So just to give you a little bit of background as to how this whole research got started, it's because I'm part of a center called the Center for AI and Society at USC that we started a few years back, I guess in my second year at USC. And that's a joint interdisciplinary research center between the schools of engineering and social work at USC. And our mission is to collaborate with communities for a more just, healthy, and sustainable world. And at the high level, what we do there is we try to revisit pressing societal problems that some community partners are faced with and try to address them using techniques from operations research and artificial intelligence, and in particular, basically by developing, by doing new research, basically, to help tackle those problems. In my research group in particular, we take what I like to call an end-to-end research approach. Basically, most of the problems that we study in my group start from discussions with community partners and policymakers. And effectively, we ask them, what are the big problems that are keeping them up at night? If there's the one big problem they could solve, what would that be it? And so with my research group, after discussions with our partners, we go away and typically formulate what are typically decision-making problems as mathematical optimization problems that are also informed by any data that our partners have collected over the years to help inform those decisions. Unfortunately, right, these are real-world problems. This is real-world data, so everything is really nasty in some sense and difficult because we have to make decisions under uncertainty. The data that we have is usually far from perfect. And so to help inform our mathematical models using those data and knowing that our decisions will have to be implemented under uncertainty gives rise to basically really hard mathematical optimization problems. And so a lot of the effort in my group goes into trying to devise tractable approximation schemes or efficient solution approaches for solving these problems. And usually these techniques that we devise can also be applied to other problems beyond the ones that actually motivated the work. Our ultimate goal is to use our solution methods to actually make a positive impact on society, effectively deploying our solution to the open world. So today I'd like to focus on one specific part of a project, I'd like to call it, that's motivated by the terrible homelessness crisis that we are faced with in LA. Just to give you a few of the numbers that are from the Los Angeles Homeless Services Authority, the entity that's in charge of allocating housing resources in all of LA County, the data goes as follows. As of the latest homeless count and housing inventory count in 2020, in January, over 66,000 persons are experiencing homelessness, and only 29,000 housing units are available to help support those individuals. But also, so not only are these numbers terrible because we see that we have significant resource shortages, actually also homelessness disproportionately affects certain groups. In particular, Black people, for example, are disproportionately affected by homelessness. They represent 40% of the homeless population and only 9% of the general population. These are numbers taken from the Committee on Black People Experiencing Homelessness, a committee that was put together to help precisely evaluate the disparities in homelessness in LA. So these numbers actually motivated our collaboration and our partnership with the Los Angeles Homeless Services Authority, where we're trying to find ways to better match individuals experiencing homelessness to these very scarce housing resources. Basically, we not only want to evaluate the current system to understand if it's doing what it should be doing, but we also want to design new and better mechanisms for allocating these very scarce resources. The person on the left down there is Eric Rice, who's the director of CASE and a professor in the School of Social Work. He's a very close collaborator of mine on this project. He specializes in homelessness, and in particular on youth homelessness. So for us operations research people, what is the problem at hand? We have resources of different types. So not all resources are the same. There's roughly speaking 3 types of resources. The most supportive kind, which is called permanent supportive housing, something a little less supportive called rapid rehousing. So contrary to permanent supportive housing, which is has indefinite duration, basically you can stay housed in a permanent supportive housing resource forever. In rapid rehousing, on the other hand, it's a shorter term, 3 months voucher-based intervention to help you kind of get out of homelessness with a little bit of support. And finally, we have services only, which effectively don't give you a housing resource, but just mental health, substance use services, and so on. And what we would like to do is to match these resources to people of different types. We can think of these people as belonging in different queues that correspond that can be formed based on their personal characteristics. And so really a policy, what it would be is a matching in this queuing system, which decides who gets what kind of resource. So how does the current policy work? In the current policy, when you come in the system, you answer an assessment, basically, which is a questionnaire that consists of a single of somewhat personal questions that ask you about your history of lived experience and so on. Depending on how you answer those questions, you receive a vulnerability score, which is basically obtained by summing up the scores that you get for the individual questions. And this vulnerability score is meant to predict how likely or not you are to exit homelessness if you do not receive any kind of housing resource. Depending on how you score, now you are partitioned, you are directed towards an appropriate kind of resource, with those that are the most vulnerable, so the least likely to exit homelessness on their own, being directed to permanent supportive housing, the most supportive housing resource, those that score in the middle being directed to rapid rehousing, and those that score at the bottom receiving services only. I would like to say that this does not mean that you will get those resources, or it may mean that you will get them, but in a very, very long time because of the scarcity of the resources. The main drawback, though, one could argue, of this policy is that it is not tied to outcomes. It looks like what we want to do is support those that are the most vulnerable, right? To kind of try and help them exit homelessness. But we don't necessarily know that the people who are the most vulnerable need the most supportive kind of housing resource. And we don't know that people who are not too vulnerable don't ultimately need a very supportive housing resource to exit homelessness. So for me, the main drawback of this policy is that it is not tied to outcomes. So in our first meeting with LAHSA, they highlighted to us that, they would like to have a policy that is somewhat better tied to outcomes and achieves certain goals, right? And they highlighted in particular that there's kind of three characteristics that they would like their policy to have, this new policy that we would like to design for them to have. They would like it to be fair, they would like it to be efficient, and they would like it to be interpretive. These sound wonderful. However, you will agree with me that they're very hard to define as well. Fairness means different things to different people. We could mean fairness in opportunity, we could mean fairness in outcome, we could mean fairness by race or by gender. Efficiency as well, it's not so trivial to define because actually people typically follow very complex trajectories in and out of homelessness. And so if I measure kind of efficiency by the number of people who have exited homelessness after a year, or the number of people who stay housed for a particular period of time, I could get very different measures of efficiency. And similarly for interpretability, someone may say that, the only way to be interpretable is to have first come, first serve policy. Others could argue that having a scoring rule is actually interpretable. And so what LAHSA told us is that actually a recurring issue in their meetings, in their policy committee meetings where they try to make decisions about how to improve the current policy, is that they really don't know what it is that they want from this policy in the end. And they would like a mechanism that can help them understand, even before going to the policy design part, understand what it is that makes a policy desirable, right? What makes a policy better than another one. And so what we propose to them is to find a way to elicit their preferences by trying to ask them a moderate number of what is called in preference elicitation pairwise comparison queries, meaning that we're going to be comparing, in this case, outcomes of different policies that we're going to choose, hopefully strategically. So let me give you an example here. We have two policies, policy A on the left and policy B on the right. And this shows like a few of the outcomes that we could be looking at. Here, I'm just showing overall exits from homelessness. So for an arbitrary individual in the population, and then probability of exiting homelessness by race for both policies. So what you can see is that the policy on the left is very efficient in some sense. You have almost 75% chance of exiting homelessness, but it's quite unfair in terms of the outcomes at least, right? Maybe in terms of the way in which it allocates resources, it could be perfectly fair. The policy on the right, on the other hand, is a lot less efficient. However, it's also a lot more fair. What we're trying to do here is, let's say I ask you, do you prefer policy A or policy B? For example, Jonathan, what do you say? Which policy looks better to you?
Hold on, I need to unmute myself. All right, figured it out. I'd say show me the Pareto optimal curve, Phoebe.
Aha. Well, so I guess these policies are designed as optimal policies for allocating resources, right? And this Pareto curve actually is like super high dimensional, right? There could be like a huge number of features. So visualizing it actually gets quite hard. I'm sorry about the background, San. So So you could, so the question, right, of which one we prefer is something very subjective, and Jonathan may say that he prefers one kind of policy, where someone else may say they prefer a different one. I think I'm getting a message. Oh, Jeff says he prefers policy A. He's very selfish, he says. Fair enough. So these are policymakers that are going to be deciding, Jeff. So in principle, you know, they don't have a stake in it. And in general, kind of the individuals that belong in these policy committees belong from in very diverse groups. And so they may have diverse opinions. We can get to that later. So in any case, by asking pairwise comparisons of this type, I can try progressively to understand what it is that you prefer. So if you say you prefer the policy on the left, then I understand that, you know, efficiency actually matters a lot, and that you are willing to sacrifice quite a bit of fairness to get efficiency, okay, which is actually a defensible point of view. The issue, of course, is that we have a huge number of policies that are possible, and going to Jonathan's point, right, there's like so many options, each of them with like a large number of possible outcomes, and so it makes it very hard to actually decide even which questions I should be asking you to try and get to the bottom of here is what your preferences are and here is the best policy for you. The problem, of course, is that, you know, if there's so many questions, I can't possibly be asking all the pairwise comparisons, right? If you think about a case where I have like 50 policies, the set of all pairwise comparisons, like 50 times 49 or something, is really huge. So what have people tried to do? There's actually a huge literature in preference elicitation from various communities, in marketing in particular, in artificial intelligence, and in operations research more recently. Broadly speaking, these streams of literature can be broken down in two categories. The first one takes a stochastic viewpoint, whereby the kind of preferences, usually modeled as utility functions, are modeled using distributions. So a priori is postulated on the distribution of the utility functions. And the second set of methods is what is called polyhedral methods, where this takes a point of view more akin to what, like, I would think of as robust optimization, wherein the uncertainty is not modeled using distributions, but rather sets. And we say that we know kind of the support of the distribution of the utility function only, and that's it. Although I'm going to take a modeling approach inspired from the polyhedral method, there's a key difference between these literatures and what we propose. The key difference is that in our approach, we're going to try and select questions to ask in a way that is informed by the downstream recommendation problem. What does this mean? It means that depending on what the downstream recommendation problem is, I'm going to be changing which question I ask. On the contrary, these approaches all try to effectively reduce uncertainty or reduce some measure of uncertainty. And this means that they may end up asking questions that are actually suboptimal, so that far more questions are needed than using our method. At least that's the hope. That's what motivated our work. And why was this important for us? Because we can't be asking policymakers like hundreds and hundreds of questions. It's really important to ask the best possible questions so that we can get to the bottom of what they want as fast as possible. So what's our proposed model? So first of all, let me introduce my model for the candidate policies, or items, sometimes I'm going to call them. Remember, roughly speaking, an item or a policy is going to be characterized by its features, which is basically a measure of interpretability, efficiency, or fairness, for example, in our context. And I'm going to collect all these features in a feature vector, and I'm always going to call my features X, which are going to live in some j-dimensional space. In order to build my pairwise comparison queries, I have access to what we call a query set, which is just a set of candidate policies that I'm allowed to choose from to build comparisons. For example, in this case, I could ask my policymaker to compare the third policy and the last policy, the ith policy, and they would answer, for example, oh, I prefer the third one. So this is my query set. And we have this comparison set C, which is just the set of all possible indices of policies that I can be comparing. Okay, so here it would be, for example, 3I is an element of this set C, and I'm asking that. Any questions so far? I have a chat. The set of categories is already a decision. I don't understand the question, actually. If you want to clarify?
It was coming right after Jeff's question, where you had given race as a category, but there are many other ways you could
Beautiful,
define.
yeah. You're absolutely right. That's a great point. Yeah, we assume that we have built a set of features that we deem are important. In order to build that set, we actually ask our policymakers what they think would be like important measures that they want to look at. And in fact, if you look like at the kidney allocation system, the way in which policies are built for allocating kidneys for transplantation, they similarly look at various metrics and they compare policies in terms of those metrics. So this is a method that's kind of like well understood. You're right that in principle, there could be then things that we include in there that are actually not useful. The fewer you have of this type, the better, because then you can learn faster. Yeah, great point. Thank you so much. So we have our comparison set to build the comparison queries, and then we have our recommendation set, which is the set from which we can use policies to actually recommend to our policymakers. We're gonna assume that this policy can either be like a discrete set. For example, it could coincide with our query set, or it could be some polyhedral set, some intersection of polyhedral set with like some integrality constraints and whatnot. And what we would like to do ultimately is to pick the best element from this recommendation set to recommend to our policymakers. But remember, we have the opportunity before making our recommendation to ask this moderate number of queries. We're going to assume that our user is rational in this presentation. This is just to minimize my notation. In reality, we can relax our assumption in our models. And we're going to assume that we can represent user preferences using some unknown utility function that's going to map the features of the items to a real number. The higher that number, kind of the more desirable the policy. I'm going to say that policy X is better than policy Y if and only if the utility of X is greater than the utility of Y. This is again assuming rationality. And similarly, I'm going to say that X is similar to Y if and only if the user has the same utility for both policies. So far, so good. So now, as I mentioned earlier, I'm going to prefer working with uncertainty sets, meaning sets of possible realizations of my utility functions rather than distributions. The reason is very simple, that it seems really hard to build even a prior, because typically we don't have any information about what the preferences of the policymakers could actually be. Building an uncertainty set, on the contrary, is quite simple. For example, if I have no information, I could say that they belong in some box. I'm going to give you more information about this in a moment. And this approach has actually been taken in a stream of papers in artificial intelligence, in marketing, and in OR. So we start with an initial uncertainty set that I'm going to call U0, which collects all the possible values that the coefficients of my utility function that I assume is linear can actually take. Now you're going to tell me, Phoebe, this assumption of linearity is crazy. This is actually a very common assumption in the literature. And it is, in my view, very reasonable because always pretty much you could kind of bring in any nonlinearity in your utility function by just constructing more complicated functions of the features, basically increasing the number of your features by taking nonlinear functions of the original features. And again, remember here I'm making the assumption of full rationality. In reality, these utilities could be perturbed by noise. That's perfectly fine, and our approach will work in that case too. We're going to assume that the set of possible utilities is polyhedral and takes this form. The details are not important, just that it's polyhedral. Some examples, if I have no information, are that my set of utility vector coefficients lie in the -1, 1 box, or that the utility of all items, for example, must be between 0 and 1. We're now ready to build our comparison queries and to try and see what happens as I start asking comparison queries and getting responses. Let's say I can ask K pairwise comparisons. So basically, I'm going to denote my kappa comparison by iota kappa for its first element or first policy, and iota kappa prime for the second one. So here I'm basically comparing these two policies, iota kappa and iota kappa prime. Once I ask such a query to the user, they have 3 options for each question kappa. They can say that they prefer the first policy over the second, that they are indifferent between the two, or that they prefer the second policy. I'm going to encode this choice using a scenario with S kappa being 1, 0, or -1, depending on the response. And I'm going to denote the set of possible responses, or encoded responses, I should say, calligraphic S. Obviously, if I ask K questions, there is S, like they must belong in the set SK. What happens now as I ask queries? Let me illustrate this with a small example. Here, I'm going to work with 2 features. I have 3 items that I can compare. And so both my vector U and my feature vectors lie in the 2-dimensional space. My uncertainty set is this -1, 1 box initially. And here I've plotted my initial items, so they're features basically. I'm going to be comparing items here. So really what matters are the vectors that take the pairwise comparisons between the features of each of the items. So for example, the vector x1 minus x2 is plotted here and so on. Now, let's say that I ask you, do you prefer item 1 or item 2? Basically, I'm asking you on which side of this hyperplane does your utility lie? If you tell me I prefer the first item, then it means that your utility vector lies in this green space. I can continue asking you questions in this fashion. For example, do you prefer item 1 or 3? If you say I prefer 3, I know that your utility vector lies in this space. So the more questions I ask you, the more I refine my knowledge about where your utility vector lies. I'm going to denote the final set, the one after I've asked you all the queries and seen all your answers, by U of iota S. This is to emphasize that this updated uncertainty set depends on both the queries and the answers I have seen. So it is a decision-dependent set. In particular, we can give an analytical expression, right, which is that it's the original uncertainty set augmented with K constraints, one for each question I've asked you, whose sign depends on the answer I received from you. Any questions? All right. So what is our ultimate goal? Our ultimate goal is to make a good recommendation. Of course, we don't have distributional information, so it makes sense to try and make a recommendation that's going to have the highest possible worst case utility, where the worst case is now taken not over the original uncertainty set, but over the updated uncertainty set, the one that incorporates your the questions, the information I got as a byproduct of the questions I asked you. We could, of course, think about a slightly different problem that's try to to make recommendations that have low regret. So in this case, we would solve this problem, which tries to minimize the maximum value of the regret, where regret is nothing more than the difference between the utility of the best item I could have recommended to you had I known your utility, and the utility of the item I actually recommended. I'm going to focus in this talk on the top problem. However, we study the bottom problem as well in the paper, so you can have a look if that's what you're more interested in. In this paper, in this presentation, I'm going to study two elicitation approaches. One is offline elicitation, where I'm going to select all questions before seeing any of your answers. And the other one is online elicitation, where I'm going to ask you one question at a time and adapt my questions to the answers I've seen from you. Offline elicitation is actually relevant when I'm when I have, say, a paper-based survey, where I need to have decided in advance all of the questions I'm going to ask you, and I can't like use a computer to kind of update the questions I'm going to ask you in response to the answers I see from you. It's also relevant if I have a bunch of people I want to ask questions to, and they should all get the same questions. In general, it's possible to use when we don't have access to a computer, basically. So in this problem, we have a two-step kind of process. We decide which policies to ask about first. We observe the answers to the questions, and then we make a recommendation. So if you want, in the problem I illustrated before, where I'm trying to make a recommendation, we want to explicitly incorporate the previous stage where I'm making questions, right? And seeing your answers. And this is precisely what we do. So we can formulate the true problem we want to solve as a 2.5-stage robust optimization problem, where today we decide on the set of questions or pairwise comparisons to ask, the IOTAs. We then observe the answers to the questions, the S's, and finally, we solve our recommendation problem. And so here, what we observe is that the recommendation problem and the elicitation part, they work hand in hand to help one another. And they're trying to make decisions, to make questions and recommendations, even when kind of the answers we receive are like not as informative as we wish they could be. So I call this a 2.5-stage robust optimization problem. I think this is standard nomenclature from like stochastic programming, where, you know, usually you have decision, uncertainty, decision. And here we have another kind of half of a stage where we have uncertainty that's revealed again. This problem, maybe I should explain what this SI actually means. So before I introduced the set calligraphic S, and I introduced also SK, which is the set of possible answers to each of the queries I have asked. Naturally, it does not make sense to give answers that are like inconsistent if we are in the rational setting. Really what we want to say is that the answers should be compatible with some utility vector in the uncertainty set. Otherwise, you're just giving me like rubbish answers that are really like not useful. So the key message here is that this formulation that we have, which sets us apart from the literature, is that it integrates the questions to ask with a downstream optimization problem. So how hard is this problem? You know, at the high level, this guy is decision dependent. It says that we can choose S such that this set is not empty, which sounds pretty complex. This guy is decision dependent, and it involves strict inequalities, because if you tell me I strictly prefer item A over item B, then I have a strict inequality in there. So it does sound somewhat hard. It's a two-stage robust problem, but with these decision dependent uncertainty sets and with large numbers of scenarios. We have the following theorems. The first says, if the recommendation set is convex, so if this guy, where I'm choosing what item to recommend, is convex, the problem is polynomially solvable and there is no benefit in asking any questions. On the other hand, evaluating the objective function of this problem is NP hard, even if the recommendation set, so again, this guy, consists of only 2 items. So this motivates us to try and find a way to reformulate this problem as some form of like MILP. And this is indeed what we do. we actually show that this offline problem, the 2.5 stage robust problem, is equivalent to an MBLP, a mixed binary linear program. What's the idea of the proof? We first show that we can actually drop the dependence on iota here, because it would never be relevant for nature to choose scenarios that make this set empty. And then we show that we can actually close this set without problems, still maintaining the same value. And we also show, in fact, that we can eliminate the responses that are indifferent, because it would never be relevant for kind of our respondent, or for what I call nature here, to answer that they are indifferent, because it would give more information intuitively. So this is a reformulated problem. Maybe I can say a few words about how we obtain that. Having shown what I just mentioned, we can then bring this max over X here before the mean by indexing it by S. We then have a max mean problem, and we can use techniques from robust optimization with endogenous uncertainty to reformulate it as an MBLP. So this problem in principle is nice because I can put it in a solver and get an answer. On the other hand, it does involve a huge number of both decision variables and constraints. Basically, it's exponential in the number of queries I ask. However, for a moderate number of queries, which actually is what we're looking for, you could in principle solve it like this. Nevertheless, already to scale to about 8 to 10 queries start getting challenging. And so this motivated us to devise a tailored column and constraint generation algorithm to solve this problem. The idea is as follows. We start with a moderate number of scenarios in this set S tilde. We obtain an optimal set of queries for this relaxed problem to solve. And then we solve a feasibility sub-problem, which basically, as a result, it returns to us either a violated scenario S that we should include to the master problem, or a certificate that the set of queries that we had is actually optimal for the problem. And this column and constraint generation algorithm actually results in significant speedups. I won't go through it today, but I am happy to discuss them offline. Let me give you a bit of an idea of our online elicitation approach. So in online elicitation, we have a far more challenging problem, because now it's a multi-stage problem with this decision-dependent information discovery again, because each time that I get an answer and each time I ask a question from you, I can update the uncertainty set to obtain at the very end of the planning horizon an uncertainty set that depends on kind of all the history of questions I asked you and answers I received. It's very relevant in practice. Actually, as far as I know, only this problem has been studied in the literature, not the offline one, which I think is very relevant in practice. This is suitable when you are doing computer-based surveys, when you can ask different questions from each individuals, and when in general you're able to solve things online. Due to intractability, we had to use a conservative approximation approach to solve this problem. What we do is that we identify one question at a time as if it were the last question asked. So I'm going to solve my MIP from before, but with just one question. Or alternatively, we can even solve it by enumeration. When the number of items is moderate, the enumeration approach is actually really fast, and it's worth using that instead of the MIP. So let me now show you some numerical results, both on synthetic data and real data. So first, I'm focusing on the max mean utility case, so where I'm trying to make questions that are going to maximize the worst case utility of the recommendation I make. And we generated a bunch of synthetic data sets with different numbers of policies and different numbers of features, or different numbers of items and different numbers of features. Each of these plots corresponds to a different data set. On the x-axis, we vary k, the number of queries we ask. On the y-axis, I'm showing the worst case utility. I should really say worst case normalized utility, which is a number between 0 and 1, where 0 corresponds to not asking any questions, and 1 corresponds to asking all the possible queries. On the first row, I'm increasing the number of items from 20 to 40 to 60. On the second row, I'm increasing the number of features from 5 to 10 to 20. And on the last row, actually I lied, I have the same data set here. It's one data set, but I'm increasing the level of inconsistencies in the responses I get from 0.1 to 0.2. From 0, I guess, to 0.1 to 0.2. Our approach is the red approach. Here we want to have high utility, so we want to be as high as possible in the graph. There was no other approach in the literature to compare to, so what we're doing is we're comparing to asking questions at random, which basically, let's say I want to ask like 5 questions, I'm going to ask 5 questions out of all the possible questions I can ask, and I'm going to do this 100 times. And I'm going to evaluate how those random queries do. Using our method, there was no other method in the literature for kind of evaluating the performance of random queries. So the range of the blue approach is basically corresponds to different random sets of questions that are asked. What we can see is that we are consistently better than asking random questions. In terms of solver time, then is the question, well, can I just evaluate the performance of all possible random queries? This is what is shown in this plot, where the graph layout is exactly the same. However, this time on the y-axis, I'm showing runtime. What we can see is that, yes, our approach takes a lot longer than, it takes an order of magnitude longer than the random approach. However, because the number of random queries is so huge, right? For example, here 60, I would have to ask 60 times 59 queries to find the best possible choice. Actually, it's definitely worth using the optimizing over the choice of queries rather than just evaluating random queries. We saw also this in the previous graph, actually, where for 100 queries, you could never find the best set of questions. Now, let me show you some results on the online elicitation. Here, there were a bunch of approaches that we could compare to. We keep our approach, the red one, the blue approach, random, and then 2 approaches from the marketing and the OR literature that are similar actually also in spirit to those from the AI literature. At the high level, what they do is they select queries that pass from the analytic center or as close as possible to the analytic center of the uncertainty set, and that kind of split it in 2 regions that would be kind of as small as possible so that no matter what you answer, we have as little uncertainty as possible. So they're very like intuitive in that sense. However, because they are completely decoupled from the recommendation problem, they result in recommendations that are not as good, although perhaps they may have less uncertainty, like smaller uncertainty sets in some sense. So what we see is that actually random seems to outperform many times these other elicitation approaches, interestingly. The way in which these elicitation approaches differ is they differ, in fact, in the recommendation step. One makes a recommendation that is as close as possible to the analytic center. Again, the rationale being that if you're close to the analytic center, you're going to be robust. And the other really optimizes to make like the robust problem to make the recommendation that has the highest worst case utility. You can see that some actually have a utility outside of the 0-1 range, which seems weird. The reason why this happens is because just the recommendation is suboptimal. So even if you ask plenty of questions, you could end up making a really bad recommendation if what you're trying to do is optimize the worst case. This figure shows the rank of the recommended item. This is not something that we optimize for. However, it's interesting to see that our approach consistently recommends items that are ranked higher. I forgot to mention one thing in my previous graphs is that when we have uncertainty, of course, we can learn a lot less because we don't trust that much the answers that we receive from the user, yet we can learn still better than the random queries. So I went a little bit back. Let me go back to where I was now. All right, so now let me give you some our results on real data, which is like going back to the problem that like motivated this work to begin with. So here we used data from the Homeless Management Information System, which is a database that collects information on all the individuals that were waitlisted for housing resources in the LA area. It collects information on what resource they received, and then information on the outcomes as a result of that intervention. So did they exit homelessness or not? Did they go back to homelessness, and so on? We grouped individuals into queues, as I was saying at the beginning of the presentation, based on their score and race. And so with this model in place, we can visualize a policy as basically the topology of this graph, which matches different types of individuals to these different types of resources: permanent supportive housing, rapid rehousing, and services only. Using this model of a policy, we simulated the performance of 50 policies, which were randomly generated, and that included first come, first served policy and the current policy in place. We needed to be a little bit thoughtful here about the simulation because this data set is observational, meaning that treatments were not assigned to individuals at random. And so actually evaluating the performance of a policy that is like a counterfactual policy is actually a non-trivial task. In any case, for each of these policies, we recorded 21 features. And we then run our preference elicitation approach on these policies. These are the results. So here we optimized regret, just to show you a little bit results for regret. Here we want to have regret that's at as low as possible, so we like our graph to be as close to 0 as possible. And we compare again for the offline elicitation case to random questions. As you can see, we have a regret that's like decreasing fast to 0, although we have 50 policies, so 50 times 49 pairwise comparisons we could ask. By asking just 10, we have removed kind of like 2/3 of the uncertainty that we had, or we're able to make a recommendation that has like 1/3 of the regret. The runtime results are similar to the synthetic case. Again, no issues there. We also evaluated our approach on the online setting. And what we can see again is that actually in this case, interestingly, the regret of our approach goes to almost 0 by asking just 10 questions out of this huge number of questions, although the other approaches linger closer to 1. And again, we're able to make recommendations that are ranked very high. With just 7 questions, we're consistently able to make a recommendation that ranks 1. We are looking to deploy this approach in the real world. It's taken us a little bit more time than planned due to COVID. We received the IRB actually yesterday, finally, so we're going to deploy in the next couple of days. What this does is first it gives you a little bit of training, and then you can begin answering questions. On the left, you're shown one policy, on the right, another policy, and you're asked to choose which one you prefer or if you're indifferent. We have 2 types of questionnaires, the adaptive and the static one. And as you answer, the adaptive one can start giving you more relevant, more and more queries that kind of get to the bottom of what is your preference so that I can make the best possible recommendation for you. All right, this brings me to my conclusion. So I hope that I was able to share with you that actually new research in optimization and machine learning, I suppose, is needed to address important societal problems of our time. I talked about homelessness. We have a bunch of other problems in other topics. For example, very related is a new project we have in collaboration with the LAC plus USC Medical Center and with the head of the medical ICU there, where we're trying to generalize this approach to the problem of eliciting the preferences of multiple stakeholders to help prioritize patients for scarce healthcare resources such as ventilators. They also feel that they have a shortage of human resources that they would like tackled in the same way. We also have, so this project dealt with kind of robust optimization with decision-dependent information discovery. We have another project that's related in the sense that it has similar The original model is similar because it involves decision-dependent uncertainty. This is in collaboration with Panthera and is concerned with helping preserve wildcats in Latin America. Intuitively, their way, we have endogenous uncertainties that we're trying to decide which parcels of land we're going to protect. And depending on which parcels you protect, then they won't be able to become developed by humans in the future. And so you're affecting kind of what can happen in terms of the uncertainty realizations there. I hope to have conveyed to you that these techniques can help solve some of the most pressing problems of our time. There's so many more actually interesting use-inspired research questions that we're looking to address. I mentioned multiple stakeholders, but there's a bunch of issues related to uncertainty in the data. For example, right now I'm taking as given that the data from the homelessness management information system is actually like 100% correct. But there's many issues that we're coming to realize exist because, for example, people are asked these very personal questions from people they don't know, like total strangers. And so they presumably believe that this data that they're sharing with these strangers may be used against them. And so they tend to answer kind of conservatively, no, I have no problems, I have no problems, when in reality they may have issues that are not shown then in the data. There's issues of missing data. We know, for example, that many of the interventions that were actually received by individuals are not shown in the data. And of course, as I mentioned, we have the issue that we have like observational data where treatments are not assigned at random, which kind of make the problems even harder. So we have a bunch of projects that try to look at these questions. This project was supported originally by the USC Zumberge and Diversity and Inclusion Initiative, and more recently by a grant that we have received in collaboration with the California Policy Lab to actually help redesign and evaluate the system for allocating housing resources in all of LA. So we hope that through this support, we will be able to really mitigate like biases and any disparities that may exist in the current system and improve its efficiency at the same time. These are the references I used for my talk. Thank you all so much for listening. Thanks, Jim. And I have a question in the, thanks, Laura. Yeah, wildcats and OR, yes, please. More coming soon on that. Yeah, I'd be happy to take questions if you have any.
I have a question.
Sure.
So first of all, good talk. Actually, cool algorithm. What I'm wondering is, so the focus here seems to be about eliciting feedback from policy-making stakeholders.
Mm-hmm.
Let's say you turn it on its head and now you want to elicit feedback from like the community.
Yeah, very good.
Right. So what do you think would be different in an approach where you're trying to get buy from a community stakeholders as opposed to policy-making stakeholders?
Yeah, that's a really great question. So this is only part of the puzzle. So first of all, we have put together a community advisory board, thanks to my colleagues in the School of Social Work. And we're using this community advisory board to help inform the questions that we actually answer. And you're absolutely right. This only gives like a small slice of the answer. And here I've been talking about policy makers, but you're absolutely right. In reality, I should use the term like stakeholders. So anyone that this system affects, be it policymakers or people with lived experience, should actually be involved in this policy design process. And that's why I'm talking about the multi-stakeholder thing, because our ultimate intention is to bring all these stakeholders kind of together and design a policy that, to the best possible, tries to fairly meet the preferences of everyone, understanding that, of course, different people and people with different lived experiences are going to have like different expectations and desires from this system. And did I answer your question, Jonathan? Yeah, perfect. Anything?
This is Paul. I imagine it's going to be much more difficult to ask the client stakeholders these questions, or to even formulate questions that you will ask them.
Why do you think that?
Well, because of the stresses they feel being clients of the system, and of the fact that you don't have any opportunity to educate or socialize them as to what the whole process is.
Yeah, that's a very good question. So actually, the policy committee of LAHSA involves already people with lived experience that are quite familiar with how the process works. And they are already involved in discussions around like modifications of the policy, changes to the current policy, issues with the current policy. And in fact, they act like as mediators in some sense, like,
but that means it's mediated. It's not the direct response of the
You're
people.
right. Yeah, you're right in that sense. In the current way in which things work, it's not like we take the voice of like 1,000 people. Yeah, they act as representatives. You're absolutely right. So I'm not necessarily trying to fix that because this is not my position. But you're right, perhaps a better system could involve everyone's voice. Right now, it acts by like representatives, and these are people with lived experiences, and there is a very conscious effort to also involve people like with diverse characteristics, so different people from different races, people from different ages, to make sure that there's representatives from kind of all groups. But you're right, this is like by no means perfect. What we're trying to do here is to find a better way that these committees can work, because realistically, even the task of making just so few people, right, understand what they want and designing something that they like already is like super challenging, actually.
Yeah. Thank you.
Thanks for your question. Yeah.
Hi, Phoebe. I have a question. A really interesting talk, as usual. I was really interested in the part about where there could be, excuse me, uncertainty in the responses that are given when you do the elicitation, because I can imagine that's a real issue, right? I mean, if you're given lots of these things, especially I can imagine some of these queries you're asking people are difficult, right, for them to make that assessment of do they prefer one or the other. So, you know, if you give the same one to somebody a week later, they might answer it the opposite way.
You're absolutely right.
And so, you know, and as you said, I mean, it does get more challenging in that environment. So I'm curious if you have thought about, you know, are there different ways to try to do better in that setting, or is it kind of a fundamental limit when that's happening that you maybe can't?
Yeah, so let me first answer how we do it, and then we can discuss whether there are better ways to do it. So in the kind of regular literature, what they do is they say there's a maximum number of like out of K queries, there's like, you know, one of them you're going to answer wrong, or two of them you're going to answer wrong. We felt that this is somewhat artificial. In the sense that, you know, it's not arbitrary, the questions that you're going to get wrong, right? Maybe this is a good figure here, sorry, this one, yeah. It's not arbitrary which questions you're going to answer like wrong or inconsistently. It's just that if you know, if you tell me I prefer item A over item B, it can't be that you strongly prefer item B over item A. It's like, yeah, even if you prefer item B, it would be not by a lot. And then indeed, like one day after another, your preferences like could change, right? And so the way in which we model it is that when you're saying, oh, let's say here you tell me I prefer item 1, instead of building this hyperplane, we build one that's like here. And so we allow for a little bit of like margin that actually your utility vector could be on the other side, but not like super far off. We found that this works better in practice when we model uncertainty using the classical models in like choice theory. That makes sense because then you have like basically you add to your utility like a bit of a noise, and then depending on the variance of the noise, you can build like a confidence interval or like how much uncertainty you allow. Now, is it perfect? Well, in simulation, it looks good, but I'm going to tell you the right answer, like the true answer when we do it in the real world. The fear there is that so long that as I allow inconsistencies, even if the user is like super inconsistent, let's say they answer completely garbage, I am still going to be trusting their answers, and this set is not going to be getting empty. It's just going to be getting smaller still. So it could be that if you kind of underestimate the amount of inconsistency, you learn you learn things that are not necessarily right. On the other hand, if you overestimate it, you're very slow at learning. So there's like this fine kind of balance. And you're right that it would be great to have a way like to calibrate kind of how much uncertainty, how much inconsistency should I allow for, but I don't have a right answer to this. So any ideas that you may have are more than welcome.
Okay, I have no idea, but interesting. Yeah, thanks.
Did I answer your question somewhat?
Absolutely. That's great.
Any other questions? All right. It's 11 anyway, so I guess we will start to have to run. Thank you for your messages, everyone. All right, Jane, I don't know if you want to take over from here.
I think maybe we're entering 1 o'clock here, and so this is our hour for the student meeting. And so I believe, Phoebe, I'm going to turn host privileges back to you. And
sounds good. Thank you all
Zach.
so much for joining my talk. I really appreciate that you being here, and thanks for all the questions.
Thank you.